charger, and there was a flyback converter. So if you have a faulty cell phone charger or a faulty laptop charger and you can open it, you can see that you see a transformer there, like a big choke, a big coil there. So that's basically this transformer, and you usually have a bridge, a full wave bridge that does the rectification for us, and then goes to the flyback converter to convert it to a different voltage level. As I mentioned already, the multiple output, it's in low voltage application it might be good, but we have something called cross regulation. Means that because of the leakage inductance, if we expect, for example, V3 to be N3 over N2 V2, this is not always valid because of the leakage inductance. If you have multiple outputs, might not be valid. So this was all about flyback converter. Now let's talk about DCM mode of operation. It's gonna be very short. So in the DCM mode of operation, as you remember, this is the case that the current goes to 0 before the end of the cycle. So the DCM mode of operation is usually more popular because you need a smaller inductor, you need a smaller coupled inductor, and you don't need a filter inductor. So basically it's gonna be cheaper. And if I find the waveforms, I'm just gonna draw it here. So the way the DCM waveforms work, basically if we have our output voltage, a VC like this, when T is on and T is on, and V secondary is like this. Sorry, this is not V, this is V primary, V secondary. Okay, so what we basically end up with here is that our current from the primary side, this is the current of the primary side. Let's just like write I, but I'll do it in two different colors. I of the primary side start from 0 and gets to a peak. We can calculate this peak because we know the slope of this line, and we know it's for this much time, right? And then it's going to be 0 afterwards. But the current of the secondary side, it's gonna start from, let's say, somewhere here, and it's gonna reach, so it was 0 before, and it's gonna go down with the slope that we know, negative V over L, and then it reaches 0. So when it reaches 0, it stays 0. Okay, so this is the DCM mode of operation. Okay, in the DCM mode of operation, if we want to find the relationship between output and input, we do exactly the same thing that we did for buck converter, buck boost converter. So we basically assume that the efficiency is 100%. Well, this is a simplifying assumption. And we calculate P in and P out, and then we make them equal. So we make P in equal to P out, and we can find the relationship between VO and VIN, right? But before that, let me just draw the other waveforms here in more details. So this is I primary, as I did before. It starts from 0, goes to a peak. It's gonna be 0 afterward. I secondary, it's gonna be 0. It's gonna go down to 0 and it stays 0 for a certain time. So it has actually 3 modes. Okay. And V of the secondary side, in this case, it's gonna be so I'm just doing this part, not V of a secondary side. And then it's gonna be 0 when the current is 0. Right, so here voltage is first negative, so this diode is not gonna conduct, but then becomes positive, and then it becomes 0. And our flux is also like this, just goes like this, and it stays 0 for a certain time. So this is T, let's say this is T2, and this is T1, which is equal to D times T. Also, some notation that I should tell you is that some people show D and then show 1 minus D, they show it as D prime. So let me actually write it better. So D and D prime, which is the same as 1 minus D, or some people actually call this one T on and this one T off. Okay. This is D times T, sorry. That's T on and T off. Okay, now I wanted to also show you some of the advantages and disadvantages of operating in DCM. If you operate in DCM, you need smaller inductance, smaller inductive filter, and a smaller magnetizing inductance. Because of these zero current switching here, right? Zero current switching here. Let's call it zero current switching here. You remember that at this point we have switching losses, so the losses is gonna be smaller, right? Because we don't have any 0 multiplied by the voltage, it's gonna be 0. So when MOSFET turns on, we have 0 current switching. The same thing here, we have 0 current switching. That's also true for buck converter and boost converter. Now that we have seen the converter losses, we can talk about 0 current switching or 0 voltage switching. At the time of the switching, if the current is 0 or the voltage is 0, then we have less losses. Right, and this is also easy